Video 2 is about homogeneous equations and prefixes. Here is a description covered on each slide. Slide 1, definition of homogeneous equations and base units. Slide 2, derived base units examples. Slides 3 through 4, how to use homogeneous equations and base units to solve questions from AS past exams. Here we have 2 examples. Slide 5, using prefixes. Slide 6 is an application of prefixes on a past exam question. And slide 7 is how to use the volume of a coin formula to solve this question, also from the past exam. What are the conditions for a homogeneous equation? When the base units on either side of the equation are the same. Now the question is, what are the base units? So the table below shows the SI base units used in physics. Here we have as physical quantity, length, mass, time, current, temperature, and amount of substance. The base unit for length is meter, for mass kilograms, for time is second, for current is ampere, temperature is Kelvin, and amount of substance is mole. And the abbreviation for meter is M, kilograms is kg, seconds is S, ampere is uppercase A, Kelvin is uppercase K, and mole is MOL. Derived base units are mixed units from base units. The table below shows how to derive from important letters used as units from scientists' names. Here we have Newton, Joule, Pascal, and Watts. And the question is, what are the base units from these letters? So let me start with the physical quantity force. The unit for force is Newton, or uppercase N. The basic formula for force is mass times acceleration. The base unit for mass is kilograms. But what is the base unit for acceleration? In this case, we need to look at the formula for acceleration. Is the change in velocity, or delta V, over the time taken to change velocity, or the letter t. In simply put, is delta V over t. Now what is the unit for velocity? Is meter per second. And what is the unit for time? Is second. So expand into fraction format. Meters per second is meter over second. And the second here is on the denominator, so I use this fraction to show that this s is on the denominator. Now I'm going to multiply. M times 1 is m, s times s is s squared, or simply meters per second squared. The unit for acceleration is meters per second squared. Now to complete this row for force, the base units are kilograms times meter per second squared. Now let's look the base units for energy. So the unit for energy is joule, and the basic formula for energy is the work formula, because work is energy, which is force times the distance. So the unit for force from the prior row is kilograms times meters per second square. And the unit for distance is meter. When we combine all these, it will be kilograms, meter times meter is meter square over second square. Now for pressure, the basic formula for pressure is force over area. Again, the base units for force is kilograms times meters per second square over the unit for area, which is square meter. So combining all the base units here, we can cancel 1 meter, and then we have just the meter on the denominator. So kilograms over meters times second square. Power. The unit for power is watts, and the basic formula for power is work or energy done over a period of time. Work and energy have different formulas and applications in physics, but work is considered energy. So to simplify our analysis here, to derive watts to its base units, so let's look here the base unit for force, which is kilograms times meters per second square. From here, the base units for distance is meter, and the base units for time is second. So when we combine all these letters, we have kilograms, meter here with meter is meter square, and this second go to the denominator, combine with this second, and now we have cubic second. In summary, all these units that take the scientist's name, like Newton, Joule, Pascal, and watts, can be represented by its base units in kilograms, meters, and seconds. So now let me use an example from the past exam, question 2, that we can apply base units and homogeneous equations to solve this question. The speed of a wave in deep water depends on its wavelength L and the acceleration of free fall g. What is a possible equation for the speed v of the wave? And we have 4 options. Let me start with a thought process. The unit for speed, represented by the letter v, is meter per second. Meter per second. We need to look each option individually to determine the unit for v based on the equation presented. To simplify each option, I'm going to neglect the constants that don't have a unit, like, for example, 2 pi, 4 pi square, 2 pi again, and 2 pi again. So I'm going to neglect all this and be working only with G and L. Let me start with the option D. On option D, velocity here is given by G over L. What is the base units for G? G is acceleration. is meters per second square. So here is the fraction format. What is the base units for length? Is a wavelength, so it's length. So is on the denominator, so it will be 1 over m. So now what I'm going to do is I'm going to cancel those two m's, and what is going to be left is 1 over second square. So the unit for this equation for velocity is 1 over second square, which is not meters per second. So this option is incorrect. Let me go to option C. So in option C, G over L is under a square root. To remove the square root, I will have to place 1 over 2 on each variable. Okay, so by doing this, I will have to apply on the derived unit for each variable the 1 over 2, I'm sorry. So here for G, meters per second square. So I apply as a subscript 1 over 2 and 1 over 2. Now for length is on the denominator. So I will place here the m, 1 over m, and 1 over 2 right here. So what I get? Again, I can cancel those two values, two m's, because they are equal. And what is left is 1 over second square, but all these is to the half power. So when we multiply 2 times 1 is 2 over 2 is 1. So the base units for equation C for velocity is 1 over second, which is incorrect because should be meters per second. Let me go to option B. In option B, G and L, they are on the numerator and they are multiplying. So the unit for G is meters per second square in fraction format, and the unit for L is meter. So now I can multiply m times m square, and the s is on the denominator, so that will be meter square over second square, which is also incorrect because the unit for velocity is meters per second. So let's look option A. On option A, G and L are multiplying, and because it's under a fraction, again, we are going to place 1 over 2 to represent the fraction here. So which means that 1 over 2 is applying on each base units. So here is the base units for gravity is meters per second square. So 1 over 2 is over m, and 1 over 2 is over second square. Likewise, for meter, for the unit for length is meter, so will be applied for m as well. So now we are going to multiply m times m, and we are going to add the exponents. So in this case, half plus half is 1. And here we are going to multiply those exponents. So 2 times 1 is 2 over 2 is 1. So the result is meters per second, which is the same as the base units for velocity. So option A is correct. Now let's look at an example of application of homogeneous equations too in this problem. The speed v of waves on a stretched wire is given by the equation v is equal t a power of P, mu, power of Q, where T is the tension in the wire and mu is the mass per unit length of the wire. What are the values of P and Q, the exponents? Okay, so let's keep calm and think a little bit. My thought process, my first one is what is the unit for the speed? The unit for the speed is meters per second. Cool. My second thought process is I need to look what are the base units for tension and for mu based on the description. Tension is a force. So a force, the base units for force is kilograms times meters per second square. Mu is a ratio, which means that is a fraction, mass over length, because that's what the statement says here, mass over length. So the base unit for mass is kilograms, the base unit for length is meter. So now when we combine the tension and mu, evaluate the exponents P and Q to simplify everything. We have here kilograms times meters per second in fraction format times kilograms over meter. So that's what you have. This is T and this is mu. Great. So now what we are going to do is we are going to add the exponents. So this is what we got as the base units for speed on this formula. Now we are going to add the exponents P and Q and on every single base units. Kilograms, P. And then the next one is meters per second square, PP. And the mu is kilograms over meter in base units. So exponent Q, exponent M. Great. Now let's look one by one and see what's going on. So this is my final, clean it up everything to have just my final equation in terms of base units. So let's look at the first one. So the first one is my P is minus half, my M is minus half, and here on S squared is minus half. And on kilograms, I also have minus half, and on meter I have minus half. Half I'm saying minus 1 over 2. And then I notice that kilograms and kilograms, they are not going to cancel each other. What is going to happen here, we are going to keep the same base, which is kilograms, and we are going to add the exponents. And when you add minus half and minus half, the result is minus 1. So kilograms is going to be showing on the result of this expression. So I will stop here because kilogram is not in the unit for velocity, which is meters per second. Stop right there. So let's take a look on option B. Okay, option B. So now I'm going to replace the values of the exponents P and Q with minus half and positive half. And then what I have, let me look kilograms first. Okay, so this kilogram is positive and this is negative, which means that this will stay on the numerator and these go to the denominator, so they cancel each other. Great sign, because kilograms is not in velocity units. Now let me take a look on meter and second. So now this meter is negative and this meter is positive. So which means that this guy go to the denominator. So going to the denominator, what's going to happen is I will keep the base, in this case is m, and I would add the exponents. So then it will be half plus half is 1. Okay, I already see something not right because the m is on the denominator. Bad sign. Just to confirm that I'm going to the right direction, what happened to the second? So second here is multiplying by these exponents. So you'll be minus 2 over 2, which is minus 1. So then go to the numerator. As you see, when you have exponents that are positive or negative, you have to look the location on a fraction. If it's negative, so which means that you have to flip the position. So in this case, it will be second over meter, which is actually the flip way to do meters per second. So no, that's not correct. Let me take a look on option C. On option C, after doing the substitution with the exponents P and Q, what I have? Okay, so here I did a little bit more work. Kilograms with kilograms, one is positive, one is negative. So this negative will go to the denominator and cancel out. Great, kilograms is not part of this equation. So now let me look meter and seconds. So meter here is half, okay, half. And second is this guy right here. And then I have this other guy right here. So after eliminating kilograms, this is what is left. So now what's going on is that this guy here is negative, so go up being positive. And this guy stay here. So now we have m. We are going to add the exponents. So half plus half is 1. And here, what we're going to do is 2 times 1 is 2. 2 divided by 2 is 1. So now we have meters per second. So this option is the correct one. So let me look at the last one, just for one extra practice. So after doing the substitution for P and Q, I have, okay, so here I can see that kilogram is not going to cancel each other. So that is a big no-no. So I'm not even keep looking what's happening to meter and second, because kilogram will be in the result here. So option C is the correct one. Now let's take a look on how to use prefixes. Prefixes are multipliers using powers of 10, like 10 to the power. This power means a number. A number can be positive or negative. Prefixes are great to simplify large, whole, or decimal numbers. So you have a like very long number. It's not a good idea to copy the whole thing. So that's why we need to simplify the number, and we use prefixes for that. So prefixes are similar to write in scientific notation. The main difference is that some powers of 10 can be associated with a prefix or letter. So here is the list of the ones used in physics. So here is tera, abbreviation upper T, and the power of 10 is 10 to 12. 10 to the power of 12. Giga, uppercase G, 10 to the 9. Mega, uppercase M, 10 to the 6. Kilo, usually is lowercase k. Sometimes I see uppercase. 10 to the 3rd. Centimeter, lowercase c, 10 to the minus 2. Milli, lowercase m, 10 to the negative 3. Micro, that's abbreviation, 10 to the negative 6. Nano, lowercase n, 10 to the negative 9. Pico, lowercase p, 10 to the negative 12. This problem is an application of a mix between power of 10 and estimation. For each quantity, is the magnitude a reasonable estimate? Option A, frequency of a radio wave, 500. P is for picohertz. Mass of an atom, 500 micrograms. The Young modules of a metal, 500 kilopascals. Wavelength of green light, 500 nanometer. So let me work first with 500 picohertz. So 500 is the same as 5 times 10 to the second power times pico, the multiplier is 10 to the minus 12. So when we combine, is 5 times 10, 10, I keep the base because I'm multiplying, so I'm going to add the exponents. So when you add exponents, it will be 10 minus 12, which is minus 10 hertz. Okay, so now we simplify 500 picohertz to 10 to the minus 10. So is this reasonable? Let's take a look. First, the frequency is given by the wavelength divided by the speed. Now, to find the wavelength of the radio wave, we have to remember the electromagnetic spectrum. So the radio waves is the longest range of the wavelength. So range from 10, like 100 to 10 to the 6th power. Okay, so how we're gonna do now? So what if we work from the extremes and see what we get to compare with this? But we need something, we need a speed. So because it's an electromagnetic wave, all electromagnetic waves, they travel with the speed of light, which is 3 times 10 to the 8 meters per second. So we know the speed. So how we calculate the frequency? So let's do this. So the frequency of the radio wave with the lowest range will be 10 squared divided by 3 times 10 to the 8, which is 10 to the minus 6. It's not here. So let's take a look on the other extreme. The frequency now for the radio wave with 10 to the 6 divided by 3 times 10 to the 8 with the speed of light, or speed of the radio wave, which is 10 to the minus 2. All right, so what happened is that it's not in this range. So what we can say here is now for the mass of an atom is the 10 is minus 27 range in kilograms. So here we have 500 micrograms. 500 is 5 times 10 squared. Micro is 10 to the minus 6. And grams to kilograms is 10 to the minus 3. We're going to keep the base, which is 10, and add the exponents. Now we have minus 7, which is not at the range of minus 27. Now, for option C, 500 kilopascals. So let's take a look. So 500 is 5 times 10 squared. Kilo is 10 cube. So that will be equal to 5 times 10 to the 5 Pascal. So when you bring this table here, metal. So it could be any metal, aluminum, brass, copper. So as you look here, the numbers, aluminum, brass, copper, they are a whole number, but the range is giga Pascal, giga. So giga is 10 to the 9. 10 to the 9. So this will not be the correct one. So now let's take a look on option D. On option D is the wavelength of green light. So here is the light spectrum from violet to red. So the green is right in the middle. So green is 500 nanometer. So nano is -9. So if you are going through the same process, nanometer, so 5 times 10 squared times 10 to the -9, 5 times 10 to the -7. But even though this here doesn't correspond to the value of the light spectrum, the wavelength, this number here, you are required to memorize from the visible light spectrum, the wavelength from, you can say from red to violet if it will be easier for you, or from violet to red, from 400 nanometer and the maximum is 700 nanometer. So the correct answer is D. This is the last problem of this video. This question is about choose the volume of a coin formula. So let me read for you. A student uses the volume of a metal coin in order to determine the density of the metal. What is not needed in order to determine an estimate of the volume of the coin? So first let me imagine the shape of a coin. It's kind of flat cylindrical shape. So here we have diameter that also relates to radius because radius is half of the diameter. And also we have a thickness or height of the coin. And in order to calculate the volume of a cylinder, which is the shape of the coin, is equal to the cross-sectional area of a circle, which is A, times the height, which is the thickness. So in simplified words is V is equal A times H. So the area of a cross-sectional area here, the circle, is pi r squared times height. So let's take a look on the options. Option A, estimate of the diameter or radius. Yes, so we need to, in order to calculate the volume, because here is not asking for the density, it's asking for the volume of the coin. Volume, what is not needed to determine the volume of the coin. So here is the final formula for volume in this case. So would you need to kind of estimate the diameter? Yes, because the diameter and radius are related. Do you need to estimate the mass? Mass is not in this formula. What about the thickness? The thickness or height? Height is in the formula. And also you need the formula for the volume to calculate the volume of the cylinder. So the only option that we don't need to estimate the volume of a coin is